Hello, everyone. So today we're going to talk about hyperparameter tuning with Bayesian optimization by El-Ateif. So I will let him introduce himself and talk to us about his journey. So the floor is yours.
Hello guys, I'm El-Ateif, engineering student at UM6P, University of Mohammed VI Polytechnic. Happy to be here with you and to share some of my my journey in the machine learning field. I'm a student. I'm an engineering student. I like to do experiments and like this trial and error loop between trial and error. And what attracts me about machine learning is like it's a new field. Like every day you can see new stuff and new research, and like there is a real momentum in the field, and that's what attracts me to it. And today our talk will be about the Bayesian optimization and how we can use it for parameter tuning. So I will start my talk by motivating the use of Bayesian optimization for hyperparameter tuning, and then we will see how it works, and finally we'll end up by a small application of its usage. So, like a typical machine learning workflow will consist of like gathering your data, and then gathering your data, and then engineering your feature, and eventually selecting the most expressive features in your data. And then the last step will be to train your model, so you can approach a target variable or predict like a target variable. So after you have trained your model, and you have this training data, and you have trained your model, you have like this last degree of freedom when to improve your performance by tuning your model hyperparameters. Sorry, I have some technical problems here. This So this step consists of tuning your hyperparameters. By tuning your hyperparameters, I mean finding your model's parameters that give you the best performance or the best and the best performance. For example, it could be like your RMSE, your root mean square error, or for example, if you have like a classifier, you are searching for the best accuracy of your model. So you are changing your parameters till you find this set of params that give you the best performance. And for example, let's take the example of a random forest. When you have like the number of trees, the max depth, so you try to increase the number of trees, or increase the maximum depth of your trees, and see how the performance of your classifier or of your regressor change. And so you have to find this set of parameters that give you the best performance. So usually we use a method called grid search. The method grid search, where we evaluate our objective function, function in each region of our sphere. So before taking more depth in this methods, let me formalize the hyperparameter tuning. So we have this objective function, we call it f over a model n. and we are evaluating this objective function. It could be a root mean square error or an accuracy. We are evaluating it over a space of hyperparameters. So we have this theta that represents our set of hyperparameters, and this space have like it could be multi-dimensional, and its dimension is related to the number of hyperparameters that you are trying to change or trying to vary in order to get a better performance. And all of this is conditioned by the data, the training data that you have used for your model. So recall that if we change our training data, so our performance will change. So we have fixed our data, and then we are trying to find the best hyperparameters. So as I said before, we have this traditional method, and this is the method that this is a manual method that we're using. So we have, for example, this here our objective function. So we are evaluating our objective function, and we have a 2D space. So we have two parameters. For example, if you have a random forest, we have this first parameter could be the number of trees, and this parameters could be the maximum split of the maximum split. And here we are evaluating the root mean square error. For example, if we have a regression problem, and we see that here we have like low RMSO, so there is a region of optimality, and here we have high RMSO. And so we hope to find these parameters that give us the best the minimal root mean square error. So grid search consists of dividing your space into with a grid, and visiting each point in your space till you find the point that give you the minimum, the optimal objective function, or it could be the minimum RMSO or the highest accuracy if you have like a classifier. So the problem with this technique, it work better. It work well. We know that it work well in like low dimensional space, but it can't scale to high dimensional space. For example, if we have like two parameters here, and we have 100 points for the first parameter and 100 points for the second parameters, we will have like 10,000 points to evaluate. And if we add another dimension with another 100 points, we will have like 1 million points. And we can see that the number of points that we have to evaluate increase exponentially with the number of dimensions. And if we add to this the time that we need to evaluate our objective function, so if we want to evaluate our objective function and get a root mean square error or an accuracy, we have to train our model. So imagine you have like a random forest. It could take like 30 seconds, but imagine if you have a convolution neural networks that could take hours. And so we don't have the privilege to evaluate our objective function at this number of points. So another method that is used is that can work well in high dimensional space is random search. So with the random search, you just hope to get lucky and get in the space of optimality. So with the random search, you define your the number, your budget, the number of points that you want to evaluate, and then you randomly evaluate your function at different points of the space, and you hope to get a point that give you a better accuracy or a better root mean square error. So as we can see, all these methods have downside, which motivate the usage of Bayesian optimization. So if we recall to the random search, if we recall to the random search, we just sample randomly our objective function at different points, and this random evaluation are independent, and we can't there is no guidance. But with the Bayesian optimization, if we here, for example, we evaluate this point, and it give you some guidance and guide you in your search for better points that give you like better performance. So the to summarize it, the Bayesian optimization answer a major question is, based on what we know so far, which point should we evaluate next? So you can see like this Bayesian philosophy in this method is that based on our belief now, how can our belief now, or how can this added information help us to update our belief about the objective function? So first of all, I will just give you the high abstraction of a typical Bayesian optimization algorithm for finding the best hyperparameters, and then we will dive into more details about and get more intuition about it. So the Bayesian optimization steps is, first of all, you like build a surrogate model of your objective function. And what is a surrogate model? It's a probabilistic model that approach your true objective function. And if we recall, we don't have access to our objective function. We don't know our objective function, like the RMSO, root mean square error of a random forest. We don't have access to the analytic form of this objective function. So we are trying to build a probabilistic model over it to approach it at every point of our space. Then after that, after we have defined our model, we just evaluate our function, our true objective function over some points. And this data will help us update our surrogate model, our probabilistic model. So we move from a prior model that we have defined that encode our belief about the objective function, and we move to a posterior model. So this posterior model is like, if we use the Bayesian jargon, it updates your beliefs about, when you update your beliefs about a variable or about a distribution, you get a posterior that is conditioned by the data, by the new observed data. So this is the typical loop of a Bayesian optimization algorithm. You observe new points, you update your model, and then you reiterate again. So now that we know the high abstraction about our method, we will see now more details, and to get more intuition about how it works. So let us first formalize our Bayesian optimization problem. So what is our goal? So our goal is to find this point in the hyperparameter space that maximize or could minimize our objective function if we are talking about a root mean square error. So this function go from a space RD, where D is the number of hyperparameters. So if you have like 3 hyperparameters, you have 3D space to a scalar value. So its scalar value could be the root mean square error, or it could be your accuracy. So this function is expensive to evaluate. It could be like the time of training your model to get one value of your function. It's like training a neural network to get the last value of your error, or the accuracy of a random forest after training it. And it's derivative free. And by derivative free, it's that when you evaluate your function, you don't have access to its gradient. So if you don't have access to its gradient, you can't like use typical algorithms like gradient descent to guide your search in the hyperparameter space. So it's derivative free. We just evaluate our function, and we get only the image and no information about the gradient or anything else. And that our problem is like is boxed. Like we can't evaluate our objective function all over the space. So we have to to constrain it. So for example, if we are talking about a random forest and we have chosen two parameters, the number of trees and the max depth, we have the max depth. So number of trees could range from 100 tree to 1000, and the max depth, for example, could range from 2 to 10. I don't know, but you should constrain your hyperparameter space. So now that we have defined our function that we want to approach and evaluate, let's start by a simple example so we can understand well how the Bayesian optimization algorithm works, and to gain more intuition about it. So we have this simple problem. We have one-dimensional space. So we have this variable, and we are our goal is to find the x that maximize our objective function f. So we are I want to find this point. So the first step, as we have said before, by the Bayesian optimization algorithm, is to choose a surrogate model for modeling the true function f. So you have to define a prior or a probabilistic model that approach your true objective function. So it is a little bit not obvious how can we define a distribution from which we can sample function. In fact, if we recall to a simple Gaussian distribution, like one-dimensional Gaussian distribution, we can sample like real values from it. Zero, for example, this Gaussian distribution that have a mean 0 and a variance equal to 1. We can like have we can sample from it real values, and we can move to a multinomial distribution. Here we have like a 2D Gaussian distribution, when we can now not just sample one value, one real value, but a vector of values. So we can build upon this observations to build a distribution from which we can sample functions. So since our space, the space that we are from where we are evaluating our function is constrained, so we have defined our bounds like here from 0 to, for example, 5. We can see our function, the function that we are sampling, as a set of points. So we can see our function that we are sampling as only a set of vectors. So for each we can sample vectors of real values, and these vectors of real values will present our function that we want to sample. So now we have seen, now that we have explained how can we draw like function from our Gaussian distribution. So we define a multinomial distribution, and then we can sample from it vectors, and these vectors could be seen as sampling a set of functions. So how can we define this prior? So as you know, a Gaussian distribution have two parameters. Like in the multinomial distribution, have the mean vector, like the mean vector, and a covariance matrix. So for the mean vector, we will take 0 vector, since I have to emphasize that the Gaussian process, or the is flexible, and so when we are trying to update our distribution by computing the posterior, this mean will change and will not be just like 0 value. So we will initialize it with a 0 vector, but it will change when we will update it in to compute the posterior. But the the most important part of the Gaussian process is computing the covariance of our distribution. So it's like you can see it as the clever step of our Gaussian distribution is how we can set up the covariance matrix to encode our prior beliefs about the function that we want to approach. For example, if we believe that our objective function is linear or periodic or have like some curve, we can encode all this information in our covariance matrix, and can be done by what we call the kernels. So the kernel is, we can see the kernel as a similarity measure, and this measure take two vectors, like 2 points in our space, for example, xi and xg, and compute a scalar value that represents the similarity between these points. And in we can see like the kernel as the dot product. So the dot product is a special case of a kernel that take two vectors and output a scalar. So this kernel, there is a lot of type of kernels, and there's like linear kernel, a periodic kernel, and these kernels encode your belief about your function. So for example, if it's linear, you will use a linear kernel. If it's periodic, if you believe that your function is periodic, you will use a periodic kernel. So in the context of covariance, this value is present the correlation between this point xi and this point xg. So the kernel, this value will impose how this point xa it will how this point xi will affect our image in the point xg. So it's the correlation coefficient between our 2 points. So this, as I say, this kernel will help us encode our belief about it. So now we have in this step we can compute a prior from which we can sample functions that approach our true objective function. And now it is time to the second step, is to compute the posterior. So as we said before, now that we have the prior and we want to evaluate our function at some point to update our belief and to compute the posterior. So this is the beauty of Bayesian Bayesian philosophy of probability in general, is you can use new data to update your model. So in this visual, you can see our posterior distribution, and I have to emphasize in one point that when you have like a Gaussian distribution and you want to condition over some observed data, or like you have like a typical Gaussian variable and you want to condition over another variable, you still have this a Gaussian distribution. So conditioning over is like the Gaussian distribution are stable by conditioning, but also by marginalizing. So if you have like a joint distribution and you want to compute the distribution of one variable in this joint distribution, it will be also a Gaussian distribution. So our posterior distribution, it is also a Gaussian distribution. So as you can see in this visual, we have evaluated our function in this point. It's now time to compute our posterior, and as you can see in this visual, we have like this function that represents the mean of our posterior. It's like this vector that we have seen before. So a vector represents a function, a set of points. So it's a function. So this is the mean of our posterior, and this region is the uncertainty at each point. And as I said before, how can we compute this region of uncertainty? Is that if we have this joint distribution, we can compute the marginals at each point. So at each point, we can we can compute its distribution, and we get this Gaussian, and from this Gaussian we can use it to compute the level of uncertainty at each point. So now we have a model that that we can update by observing new data, and the Bayesian optimization or the Bayesian the process will not only give us like a deterministic function that approach or that approach our true approach our true objective function, but also give us the level of uncertainty at each value. So it's a probabilistic model. And that's the beauty of Bayesian probability. It's not only give you like some deterministic values, but also the level of uncertainty or error for each point in your function. So as you can see here, for example, where we have evaluated our function, we have like this small level of uncertainty, which means that in this region we have already evaluated our function, so we have gained more information, thus the level of uncertainty will be low. But in this region where we didn't evaluate our function, we have high level of uncertainty. So we still need one last step, is how can we use this posterior distribution, this posterior model, or this model that we can update with the new data that we have evaluated, to choose the next point where we're gonna evaluate our function. So for example, in this step, we want to choose the next point where we will evaluate our function. To do that, we will we will present a function that is called the acquisition function, and the acquisition function is a method, or it's a that quantify the finding the next point to evaluate. So the acquisition function is like a utility function that search for the best x in our space that maximize like our improvement. There is like different acquisition functions. So for our use case, we will use the expected improvement. What this function does, it say, hey, take the point that in expectation will increase your performance the most. So for here, we are taking the expectation of our max of a difference between our model, of our value of model, and the best sampled point that we have observed till now. So this is our definition of the expected improvements, and our goal is to find the next point that maximize this function. So now that you can see like how we have moved from a function, our objective function, that we don't know anything about, and we can't find like analytically the maximum argument that maximize this function, because we don't have access to its analytic form, to a utility function or an acquisition function that we know the analytic form, and so we can use it to guide our search. So at each iteration, after like updating our model, we have access to this utility function, so its analytic form. It's easy to find the maximum value of it using like some classical optimization algorithm to find the maximum of a function. But what is more interesting and is how this function, why this function is interesting. Is that we can like rewrite this expected improvement as the sum of two terms. So the first term, it's as we call it, the exploration like the exploitation term. So I have a mistake here, but it's called the exploitation term. So this term will tell you to stay in regions when you have already found like better you have like better performance. So for example, if I evaluate my function here, the expected improvement will tell me to stay in this region and evaluate more points because I have low uncertainty and I know a value. I know, like, I have information about this region. But there is another term of our utility function that is called the exploration term. So this exploration term, if we want like to maximize our function, we have to maximize the point with high uncertainty. So this term tell you to visit regions where you have high uncertainty. Why? Because, for example, if I found this point here, yes, it gave me like a good performance till now, but what about other regions where we have like high uncertainty? For example, this region, if I could visit this region and evaluate my function, I could like find better performance and like a better performance. So this function, so maximizing this utility, it's about switching between exploration and exploitation. So you in some iteration you want to exploit the regions that you have like better in performance, but in other iteration you want to explore regions with high uncertainty, so maybe you can find a better performance. So to see this better, I will share with you like a small a code example. Sorry. Yes. Well, so here we have like the typical coded version of you can call it a vanilla form of our Bayesian optimization problem. So at each time you update your Gaussian process model with the new data that you have observed, and then you use your expected improvement function or your utility function to find the next point that, to evaluate. So this point, then you evaluate your function at this suggested point, and you redo this iteration another time when you update your model and find the best point. So I will show you here, for example, some example. So the function that we want to maximize is this function, and our goal is to find the maximum. So in this visual, it gives us the different iteration of our model. Here we have like in blue our surrogate model, our probabilistic model with the level of uncertainty, and here in red we have our utility function. So let's see this third iteration. So our utility function in this iteration max at the point 0.3, and if we see our model, it say that, hey, visit this region where you have like high level of uncertainty. So our utility function encourage us to visit to explore regions where we have high level of uncertainty, and maybe we can find the points find the points with a better performance. For example, in this region, like we can find this point with the higher performance. But in the fourth iteration, for example, our utility function max at this point, which tell us to, yes, there is like high uncertainty here, but no, this time we'll just exploit regions that we have already visited and try to evaluate our true function here, which maybe we could find the point with better performance. and we keep iterating and iterating till our Gaussian process, our Gaussian optimization converge. Like for example, here we have converged at the same, so our utility function max at the same point, as you can see. It max at the same point, and we have found our maximum performance. So you can stop now if you, for example, define a convergence criteria to stop your algorithm. So as you can see in this iteration, the utility function, it's what's interesting about the Gaussian process. It will guide you in your search. So it's not like random search or some grid search where you visit all the points. In the Bayesian optimization for finding the best parameters, it will guide your search at each iteration. So based on the data that we know now, what's the next point to evaluate? So this is the like what it does. It uses this utility function to guide its search. So these visuals are good to see how our model works, but like with when we are working like in real application, our space, we are not like optimizing over like one-dimensional hyperparameters, but a set of hyperparameters. So we have like 3D space or 4D space, so it's hard to see our how our algorithm to visualize our probabilistic model. For that, we can use these two plots. So the first plot give us the distance between two consecutive points, so for each iteration. So as you can see here, how the model jump from a region to another region. So for example, if we like have this high hopes, so it say that our model is trying to explore some region with high uncertainty. But here we have like small distance between consecutive points, which means that our model is exploiting a region where he think that there is like high performance there, so he stick with this region. So this distance plots give you like help you understand how your model behave while you're running your iterations. And this second plot will show you the best y, or the best target, the best evaluated point at each iteration. And this show us why we use the expected improvement function, because at each iteration we are searching for the point that maximize our expected improvement. So it will help us, it will guide us to a point that will maximize our improvement. So now, after we have like grasp a higher how the model works, and we have like an intuition how it works, it's time to use it for like real application. So for this problem, we have let me go back to the sketches. So for our application, we will try to optimize or to tune the hyperparameters of XGBoost regressor. So for this XGBoost regressor, we have chosen 5 parameters, which give us and our criteria, it's a regressor, so we will choose the root mean square error. So to formalize as before, we have this function, our objective function, which is the RMSE, that goes from a space of 5 dimensions to give us a scalar value. And to stay with like because we have already we in the Gaussian in the Bayesian optimization, we are trying to maximize a function, so we will take the negative root mean square, since we are trying to minimize it, so we will take the negative root mean square error. So our model will try to maximize this function. So after we have defined our problem, so we have this objective function where we throw some parameters, train our XGBoost regressor, and get a root mean square error. So this is our objective function. This is our space. We have like a space of 5 dimensions with the learning rate, a max depth, and a number of estimators. So let's move to the code. So we have like this. We will take this toy data set, and we'll use our XGBoost regressor, and then we will use the like a cross validation, and to find like our baseline. So we'll just use like the default parameters of our XGBoost regressor, and use cross validation to find the root mean square error of our model. So to have like a comparison between random search and our Bayesian optimization, we'll first give it the space. So we give our random search the space of search, like this learning rate, the gamma parameter, the max depth, and the number of estimator. And we will use the random search cross validation of scikit-learn to find the best parameters over 25 iteration. So this first model gives us like the results of like a simple random search, and then we move to our Bayesian optimization. Here we give it, as before, our constrained box. So this set of parameters for each dimension, we give it the domain bounds. Like for example, the learning rate will be between 0 and 1, and the gamma between 0 and 5. And for the number of estimator will be like between 1 and 300 estimator. Now we have defined our bounded box, or our bounded space. Now it's time to define our function. So this function will take parameters as input and will output a score, which is the negative mean square error, since we are trying to maximize our function. So it runs at each time. So to see how it is expensive to get 1 point for our objective function, we are at each time throwing our parameters and running a cross validation over our XGBoost regressor, and then getting the mean of mean square error. So each time we want to evaluate our function, we train our model using the cross validation. And after we have defined our function, we will use the Bayesian optimization. We give it our function. So there is some libraries that have already implemented this optimizer, or you can like write it yourself to have a grasp, to have like more control about it. So it's easy to write your Gaussian, like your Bayesian optimizer. But you can use like some library like scikit-learn that have an implementation of this Bayesian optimization. So you give it your function, your domain of where you want to optimize your function, and the type of model. So we are using the Gaussian process, and the type of the acquisition function. As I said before, there is a lot of type of acquisition functions, and for our use case, we will use the expected improvement, and we give it these parameters that we call the acquisition jitter. So to keep it simple and don't get into the details, this parameter control this trade-off between exploration and exploitation. So for example, if you have like a higher jitter parameters, like your model will tend to explore more than exploit. So this is a hyperparameter for your Bayesian optimization. You can use it to guide your acquisition function or your utility function, and we tell it to maximize our function. So we give it our budget. So we have like 20 iteration to evaluate our model. So this is a graph that shows us the different iteration and the results, our results. So as you can see, the random forest have evaluated our objective function at 25 iteration. But as you can see, it's like it is stuck in some suboptimal regions where it find like 3,715 root mean square errors. It have a good performance, but it's stuck in suboptimal regions. But with using the Bayesian optimization, we have like in the first iteration we are like having like some good performance where we can like here we have like exploding, so we are getting the same score. But here we have like hopes, so we have explored some new regions where we have like some good performance. And as you can see, this you can see literally the difference between some traditional random search and our Bayesian optimization. It's random search. You're just hoping to find like optimal performance, but you don't know because you don't have access. You don't have access to all the regions in your space. You just hope to get in optimal values. But with the Bayesian optimization, there is some guidance that guide you to the best regions in your space. So, but if you want, like, if your problem is easy and you have like the time, you can use like a grid search where it's guaranteed that it will visit all the regions in your space. So this is all. Thank you for staying with me.
Thank you so much, Anas. It was really like very rich and, like very well explained. Thank you so much.
Thank you.
Like,
Thank you, Sarah.
do any of you have any kind of questions you would like to ask our speaker? Okay. So I actually, from my part, I'm curious about one thing. Like, when do you choose to use Bayesian optimization?
Yeah, so it's a good question. It's a good question. So Bayesian optimization, it's about like if you have a function that is like is expensive to evaluate. For example, let's see, for example, a convolution neural network, where you want to, for example, you are trying to find the optimal number of hidden layers, for example, or the learning rate. Like, you don't have this privilege to train your convolution neural network like 100 times. So you have like this fixed resources, and you are trying to use it optimally. So you use the Bayesian optimization to guide your search, and like you have this guarantee that you will find this optimal regions. So if your function is expensive, it's good to use the Bayesian optimization.
All right. Thank you so much for explaining that.
Thank you.
Because I know it is used, but I never really understood why. Like, why do we use it? Like, why do we not use it like usually? Why is it only sometimes?
Yeah. Why we don't use it usually? Because as I said before, in each iteration we are updating our posterior. So it's updating our posterior is it's expensive. So we have to compute each time your covariance matrix and your mean vector, and find the maximum of your acquisition function. So it's expensive. But if you see that evaluating your like true objective function, it's more expensive than evaluating your posterior distribution, then go ahead with like Bayesian optimization, and it will give you like good results.
Okay, thank you. So we have a question from the attendees, and it's from Sai. He says, how is the Bayesian algorithm different from k-means clustering?
So I don't see like how can we compare the Bayesian algorithm to k-mean clustering? But for example, like Bayesian optimization algorithm is used to approach your functions, but like k-mean, it's used to cluster your data and find like the clusters in your data. So I don't see the.
Yeah, actually, Bayesian algorithm is just an optimization algorithm, like all the other optimizer. So, for example, you can either choose to use, like, for example, Atom Optimizer or AdaBoost or whatever, or of course you can use
Yeah, it's like it's flexible. Like you just have to give it like a function to optimize. It doesn't depend on your model, or like you can write like a typical Python function that you give it parameters and you get an output, and then you feed it to your optimizer. So it's flexible to any model that you want to use.
All right. Thank you so much. Like, can you share with us these resources or?
Yes, of course. Like there is a good Google notebook that I've used for my code. It's I will I share it in the comments section.
Yeah, of course. Go on. You share it, and I will share it.
Okay. So they have implemented like a vanilla code of our this Bayesian optimization, and they explain the mathematical side of it and how they can update their posteriors. So I will share with you the Colab.
Thank you. All right.
Okay.
Thank you. All right, let me share it with them.
Okay.
Here you go. So I think because like there like a lot of people were here to support you. So would you like to tell them anything?
Thank you for supporting me. It's like as I said before, it's my first talk, and I'm happy to share with the community. Like it's good to it's a good thing to share with the community when you learn like something new. So it gives you like a momentum to learn new things and keep going in your journey.
Definitely.
Thanks,
Thank
guys.
you so much. It was an amazing
Thank you,
talk. I was happy to attend this at least. Thank you so much for giving us your time and for the amazing talk. It was inspiring.
Thanks. Thanks, guys. Thanks. Bye.
So thank you, everyone. See you.